Have you ever wondered how a search engine can sift through billions of documents and find exactly what you're looking for in like a fraction of a second? It feels like magic, right? Well, it's not. It's actually a really clever trick that's been around since the 1970s. So let's pull back the curtain on the secret shortcut behind superfast search, skip pointers.
Okay, so let's just get our heads around the massive scale of this problem. Imagine you're trying to find which documents two different words appear in. You've got two huge lists of document IDs, and when I say huge, I mean millions, maybe even billions of entries. How in the world do you find the ones they have in common without it taking, forever?
At a high level, you really only have two ways to go about this. On one hand, you've got the linear scan. This is the brute force method. Just check every single thing one by one. Slow, but steady. On the other hand, you've got a smarter scan, where you can actually skip ahead. And that right there is where things get interesting.
Now, to really appreciate just how brilliant the solution is, we have to feel the pain of the problem. So let's talk about why that check everything approach just completely falls apart when you're dealing with data at this scale.
Look, a linear scan will get you the right answer, eventually, so it is correct. But my gosh, is it inefficient? Just think about it. If you're at document 5 in one list, but the other list is already at document 100, you know for a fact that there's no way documents 6, 7, 8, and all the others in between are going to match. You're just wasting so much time. There has to be a better way.
And of course there is. This is that aha moment. The real solution isn't about working harder or faster, it's about working smarter. It's about finding a way to just leapfrog over all that useless work.
And let me introduce you to the hero of our story, the skip pointer. It's actually a beautifully simple idea. It's just an extra piece of information, a little shortcut that you embed right inside your list. It's like a signpost that says, hey, you can safely jump from this spot all the way over to that spot, because I promise nothing you care about is in between.
So what this does is, it turns the whole search into a simple two-step dance. Step 1. You use the skip pointers to make these huge leaps, navigating between big chunks of the list. Step 2. Once you land in the right general area, you just switch back to a quick little linear scan to pinpoint the exact item. You get the speed of jumping and the precision of walking. It really is the best of both worlds.
Okay, but this brings up our really fascinating question, right? How big should those jumps be? Because if you get this wrong, your clever shortcut could actually end up slowing you down. It's a really delicate balancing act.
Let's look at one side of the problem. What if you get a little too excited and put skip pointers everywhere? You make your blocks, your jumps really, really small. Well, now your algorithm is spending all of its time just checking the signposts. You're making all these tiny little hops, and you're barely moving faster than if you were just walking. That's no good.
Now let's look at the opposite problem. What if you're too stingy with your skip pointers? You make these absolutely massive blocks. Sure, you take a giant leap, but then you land in this huge area and you're stuck doing a long, slow, painful linear scan all over again. You've just traded one kind of slow for another.
And you know what's cool? We can actually describe this whole balancing act with some pretty simple math. The total time, or cost, of our search is basically two things added together. The time it takes to make the jumps between blocks, plus the time it takes to scan inside a block. Our goal is to make that total cost as small as we possibly can. So how do we find that perfect balance?
The answer is just so elegant, you have to love it. The sweet spot, the absolute perfect point of balance that minimizes our total cost, happens when the size of our block, which we call k, is equal to the square root of the total length of the list, n. It's that simple. That formula gives us the most efficient jump size possible.
All right, enough theory. It's one thing to talk about it, but it's another thing to see it. Let's get our hands dirty and walk through an example to watch these skip pointers really do their thing.
So here we go. We've got two lists, P1 and P2. And you can see we've already set up our skip pointers. For P1, it has 9 items, and the square root of 9 is 3. So our skips are set up in blocks of about 3. For P2, with 6 items, we've gone with a block size around 2. Okay, let's find the documents they have in common. Okay, round 1. Our pointer for P1 is at the number 3 and P2 at 6. Since 3 is less than 6, we know we need to move P1 forward to try and catch up. But can we skip? Well, the skip pointer at 3 wants to jump us all the way to 15. That's way past 6, so we'd overshoot it. So no skip this time. We have to take it one step at a time until
We get right here. This is the magic moment.
P1 is now at 9, and P2 has advanced to 15. The algorithm sees that 9 is less than 15. It checks the skip pointer, and that pointer goes to 15. Since where we want to jump to, 15, is less than or equal to where the other pointer is, also 15, it's a valid skip. And just like that, bam! We leaped over a bunch of steps and landed directly on a potential match.
And what do you know? It paid off. We land, and both pointers are now sitting at the number 15. We've got our first match. We write that down in our results, and we advance both pointers to keep on searching.
And from here on out, it's pretty much rinse and repeat. The algorithm just keeps doing that same dance. Compare, skip if you can, find a match, advance. It finds the other matches at 24, 39, and 68 until one of the lists just runs out of items to check. And we did it all way, way faster than just plodding along.
So, after all that, what's the final verdict? Is this old-school trick from the 70s still a killer shortcut, or is it more of a historical dead end? Let's break down the pros and cons. Well, the strengths are pretty clear. Skip pointers absolutely slash the number of pointless comparisons you have to do. For really long lists, this means a huge real-world speed-up. Plus, they're actually pretty simple to implement, and they don't take up much extra memory. Just that small square root of n amount of space.
But, they're not a silver bullet. They don't actually change the theoretical worst-case performance, what computer scientists call complexity. And honestly, you really only feel the benefit on very, very long lists. On top of that, the pointers are static. You set them up once when you build the index, and you can't change them on the fly.
So in the end, I think the big takeaway is just how powerful a simple, elegant idea can be. And it leaves you with a really fascinating question to think about. If this clever shortcut was invented half a century ago, what brilliant, simple optimizations are being cooked up right now that are going to power the technology we'll be using for the next 50 years?